When two black holes, each dozens of times the mass of our Sun, spiral toward each other, they create violent events in the cosmos. The impact is so intense, it stretches and squeezes the fabric of space itself, sending ripples radiating outward in all directions. These gravitational waves travel across the universe at the speed of light for 1 billion years. Albert Einstein predicted these waves in 1915, but he assumed humanity would never actually be able to detect them. He believed the signal would be too weak. By the time these ripples reach Earth, the spatial distortion they cause is infinitesimally small. To prove Einstein right, scientists had to build a machine capable of measuring a change in distance far less than the width of a single proton. The solution is the Laser Interferometer Gravitational Wave Observatory, or LIGO. It looks nothing like a traditional telescope. Instead, it is a giant L shape laid across the landscape. The facility uses two identical, perfectly straight vacuum tubes that each stretch for 4 kilometers. The core technology housed inside these concrete pipes is a technique called laser interferometry. As this schematic shows, the L shape acts as an impossibly precise ruler, measuring the length of both arms at the same time. A laser is the only tool stable and fast enough to act as the measuring tape for a distance this large. Finding a distortion smaller than a subatomic particle across 4 kilometers of pipe requires the most precise, isolated environment ever constructed on Earth. The process begins by firing a single, powerful laser beam into the center of the facility. A specialized mirror divides this light, sending one half down the first 4-kilometer arm and the other half down the second arm. The light travels the full distance, hits freely hanging mirrors, and bounces back. The beams trace their 4-kilometer paths in reverse and recombine at the center of the detector. Because the two arms are exactly the same length, the light waves return perfectly out of phase. The peaks of one wave align exactly with the troughs of the other, and they cancel each other out, a process called destructive interference. The result of this cancellation is absolute darkness. Zero light hits the final detector. This engineered darkness is a perfectly balanced trap, waiting silently for a ripple in spacetime to spring it. When a gravitational wave passes through the Earth, it temporarily distorts physical dimensions. The wave stretches one of LIGO's 4-kilometer arms while simultaneously squeezing the other. Because the physical distance has changed, the returning laser beams no longer arrive at the exact same moment. The waves fail to cancel each other out, and a flash of light successfully hits the detector. When physicist Rainer Weiss drafted the initial blueprint for this method in 1972, he realized it would only work if the mirrors were isolated from all other noise on Earth. To keep the mirrors perfectly still, engineers had to block out seismic tremors, thermal fluctuations, and even the quantum vibrations of the atoms inside the mirrors. Because of that isolation, when a flash of light appears in this void, scientists know with absolute certainty that spacetime has just flexed. On September 14, 2015, the trap finally sprang. The first true flash of light was recorded. The data perfectly matched the theoretical signature of two massive black holes colliding. 100 years after Einstein proposed his theory, this incredibly faint signal proved his prediction with remarkable precision. This work earned the creators of the observatory, including Barry Barish, the Nobel Prize in Physics for capturing a measurement long thought impossible. This experiment provided direct physical proof that the fabric of the universe can ripple. That first 2015 detection was just the start. Since then, hundreds of massive black hole mergers have been detected. The network has expanded globally, working with partner observatories like Virgo in Italy to pinpoint where these collisions occur. For all of human history, our knowledge of the cosmos relied on looking at the light emitted by stars and galaxies. Gravitational wave astronomy allows us to study the invisible, dark events of the universe that emit no light at all. By building the most precise rulers on Earth, we have finally developed the ability to record the resonance of spacetime,